and welcome back to another video. In this one, we're going to cover implementation of a generic linked list. If you're unfamiliar with dynamic data structures, then you can check out my slices video, or if you're uncomfortable or unfamiliar with generics, you can also check out my generics video. To start off, I will give a brief introduction to linked lists and how they work and each of their operations, but if you're already familiar with linked lists, then you can go ahead and skip through the timestamps that I have in the description. Let's get right into it. Starting off, arrays are a fixed size. Once initialized, they cannot shrink or grow, and since all elements are next to one another, large chunks of the heap must be allocated, even if not all of the indices of the array are being used. On the other hand, a linked list is a collection of values encapsulated by this node structure. Each node contains the value and a pointer to the next node in the list. We can trivially add or remove from the list without the data structure taking up extra space. Let's see how this looks in code. So we have a very basic folder structure here. We have a parent folder called ds, then linkedlists.go for our linked list implementation, and main.go where we can create our linked list, add to it, remove, and whatever other functions we create. So over in linkedlist.go, we first need to define our data structure. Now, linked lists aren't just a series of nodes. Like, we're not going to have only nodes that interface with those for the user. We're actually going to have a linked list wrapper structure. So to begin, we'll have type linked list. And since it is a generic linked list, meaning that we can hold different data types in it, we will use the T convention for a generic, and whatever data type that is given to this linked list that it will hold, it will need to conform to the comparable interface. And that allows us to basically compare the values, which are going to be T of type T, with one another. So linked list comparable, it is a struct type, and the linked list definition is very simple. We have the head, which is going to be a pointer to a node, which we have not written yet. And then we're going to have a size that is of type int. Note, I do have these in lowercase because we want to hide this implementation from the client or whoever is using the linked list API that we're going to make. But since it's currently in the main package, just with our main.go, we'll be able to manipulate those. Next, we need to create our node structure. So again, it's going to be type node. It's going to hold the type of T that conforms to comparable. It's going to be a struct, and we also have two very simple definitions within the node. First is going to be the value that it contains. So this is just like the element in an array, and it will be of type T. Then we have to hold a reference to the next node in the list. So all we'll call that is just next, and it will be a pointer to a node that also holds the type T. And so that means that we also have to go up here and fix this implementation for that node to hold type T also. And that is it for defining our structure. And from here on out, we're just going to be working on methods of the structure. When it comes to adding to a linked list, there are two cases we need to account for: when it's going to be the first node in the list, and if there are already nodes in the list. Starting with it being the only node, the only thing that we need to do is create a new node and assign the linked list head to that new node's reference. But if there are already nodes in the linked list, then we can quickly insert into the list by assigning the new node's next reference to the head of the list, then update the head reference to point to the new node so that no node is ever orphaned. This is more like a prepend operation than it is an add or an append operation. But if you're looking to append to the list, then you can just maintain a tail pointer, just like we have a head pointer. And so that all you need to do is just operate from the tail pointer and add to the end. Let's see what this looks like in code. So below our struct definitions here, we'll create a new function that is going to have a method receiver on it, which we'll call it LL, and it will be a pointer to a linked list that holds type T. And the method will be called add, and we'll take in one argument or parameter, which will be called new val of type T. So this is going to be the new element that we're going to hold within this linked list. Now, whenever you have a pointer receiver, you always have to make sure that it's not null. If we tried to access the linked list's head or size at this point, we would get a panic because the pointer is pointing nowhere. So we'll first say if LL is equal to nil. We'll just return early. We're not going to try to do any fancy messaging. We'll just return early. If our linked list is not nil, then we can create a new node out of the value that we were given as an argument to the method. So it will be new node will be initialized to a node that holds type T, and val will be equal to the new val that we were given from up above, and then the next pointer will be nil. Now, when we go ahead and create the node by default, the next pointer will be nil, even if we didn't specify it, but I like to be very explicit in my code. Now that we have the new node, we have two test cases that we need to take care of. The first is if this is going to be the very first node in the linked list. And then the other case is if we already have nodes in the linked list. So let's cover the first one. We'll say case 1, first node in list. And how we can check for that is by checking if the linked list.head is equal to nil, because the head is the very front of our list where we start and enter into the list. So if that is nil, then we have a very simple add operation. It's just ll.head is going to be equal to the new node. Then we'll go ahead and increase the size and return early. Now, if the head was not nil, then that means that we have multiple nodes within this linked list already. So let's go ahead and create a case 2, nodes already in list. And this is where we do a prepend operation. We're going to take the new node's next pointer and we'll point it to the linked list head, meaning that we're putting it before the head of the linked list. Then all we need to do to maintain the referential integrity of our linked list and know where we can start to enter it, we just say ll.head will be equal to the new node. Now the beginning of our linked list is at the new node, and new node will point to the next node in the list. Don't forget to increase the size of the linked list, and that's it. That is the very simple implementation of an add operation into a linked list. So let's go over here to main.go and make sure that this doesn't crash and burn or anything. We'll create a variable called ll and initialize it to be a linked list that's going to hold integer types. And for now, we don't need to initialize anything a part of it. Let's make sure that we can call the add function. So ll.add, we'll do 1, and then ll.add 2. We'll go ahead and save this, go down to the console, go run, and nothing got printed out. So it looks like it added these correctly. Now the contains method will introduce us to linked list traversal. Let's say we're looking for the value 2 in a linked list. We can start by creating a temporary node that starts out at the head node of the list. We'll then continuously update the temp node to its next pointer until we find a matching value, or until temp is set equal to null. If we find a matching value, we return true because the linked list contains that value, and if it ever becomes nil, then we return false. Let's see what this looks like in code. To start off implementing this, we'll have a function that's going to take a pointer receiver, so ll of linked list holding type t, and we'll call it contains, and contains is going to have one argument. It'll be val, and that will be of type t. We'll return a boolean on whether or not we find the value within the linked list. And so the first thing that you need to do whenever you have a pointer receiver is check if it's nil. So if ll is equal nil, then we'll go ahead and just return false. Otherwise, we can go ahead and go through the normal process. So the first thing we need to do is create a temp node that's going to be assigned to the linked list head. From here, we create basically a while loop. So for temp is not equal to nil. And this is where we go ahead and check the value for a comparison. So if temp.val is equal to the value that we were given up in the argument, then we can return true, meaning that we found the value in the linked list and we can exit early from this function. Now, where many programmers sometimes trip up is this loop will tend to run forever until you update the temp value. So you need to make sure you have temp is equal to temp.next. Basically, we're moving the temp pointer one forward in the linked list. Now, if we go through this entire for loop and we never find the value, then we just return false. And that is a quick version of the contains method. So let's go ahead and make sure that this works correctly over in our main.go. I will do a format.println, and we'll do ll.contains1. So when I save this and we go ahead and run this, we get true. Let's check 2. We do go run and we get true. And then we will do 3, since 3 does not exist in the linked list, and we get false. So we know our contains works fine. The remove function may be the trickiest. Similar to the contains function, we need to traverse the linked list until we find a match and remove the node upon the match. But how we do this is we need to have basically 2 temporary nodes. We'll have one temporary node that does the linked list traversal, and then we'll have a previous temporary node that is just one node behind our temporary. When we find a match in the linked list, what we'll do is we'll take the previous node's next pointer and point it to the current node that we are currently sitting at in the linked list traversal and point it to its next node. So basically we're just skipping over the node that we matched on. This will then remove the reference to the node that we are removing, and the garbage collector will later clean it up. Let's see what this looks like in code. To begin implementing the remove method, it will be similar just to how we have all of our others from up above. So we'll have a linked list pointer receiver. We'll call it remove, and we'll give it a value of type T that we need to go ahead and find within the linked list. And since it's a pointer receiver, we need to check if it's nil. So if it's nil, and we'll actually check if the size is 0 too. So ll.size is equal to 0. Then we'll just go ahead and return. Otherwise, this is where the complex logic begins. Let's go for the simplest case first. We only have one node in our linked list, and that node is equal to the one that we need to remove. So if the size of the linked list is equal to 1 and the head value is equal to the value that we were given from up above, then all we need to do is say ll.head is equal to nil, and then modify the size to be 1 less than what it was before, and we return early from this function. Otherwise, we have multiple nodes in this linked list, so now we can have a previous node and a temp node, which is also our current node. So we'll have previous be equal to the linked list head, and then we'll have temp, which is the one that will primarily do the leading of iterating through the list, and that will be equal to the head's next value. We'll do another quick check here to make sure that the head value is not nil, because we already did a check on the head up here, but that was only if the size was 1. So if the previous .val is equal to the value that we were given up above, then we just move the head of the linked list to its next value, reduce the size of the linked list, and return early. So now we've knocked out 2 out of the 3 cases here, and here's the last one. It's if the node that contains the value is anywhere else in our linked list. So this is where we do that typical linked list traversal. So for temp is not equal to nil, we'll check if the temp's value is equal to what we have in the parameter. So if temp.val is equal to the val that we were given, then we again take the previous node that we've been tracking. So previous.next will point to the temp's value next reference, reduce the size, and return. Pretty simple. But again, don't forget to update your pointers. So the previous will be equal to temp. Make sure you do this first. So now previous and temp are pointing to the same node. Then we can go ahead and move temp equal to its next node. And that's it for removal. So let's go back to the main.go and let's change this contains to 2. And before the contains, we'll do a remove call and we'll remove 2. So when we go ahead and run this, we should get false. And indeed we got false. Now instead of removing 2, let's remove 1. Let's save and run this. So 2 still exists in the linked list, but now let's change it to contains 1, and we also get false. So everything is working just as expected. And that's the basics of implementing a linked list in Go. If you're looking to test your knowledge after this video, I'll have a GitHub repository linked below where you can write your own code for a linked list and use the tests that I've written to see if you've written your implementation correctly. If you made it this far in the video, I encourage you to like and subscribe, and I'll see you in the next one.